in the midst of so many distractions in the form of webinars and seminars and colloquia, etc., we have people who are still attending our colloquia, and of course today is a very special one. We've been at this from April, and now we've moved to a situation where we have colloquium every other week, and the other Thursdays we have more specialist seminars, and of course we have various other events on Zoom at other times of the week as well. Thank you for attending, and you'll be familiar with this format now. Today's speaker is Professor Dipankar Bhattacharya, who is, of course, a distinguished professor here at IUCAA and the Dean of Core Academic Programs. I've known Dipankar from the very first days of my getting interested in astronomy. He was, I think, in the first batch of the JAP program at the ISC and did PhD. That's right, and the very first batch, which the JAP program is still on and has produced some very distinguished scientists. And of course, he did his PhD. The Raman Institute is part of that program. Then was a postdoc at the University of Amsterdam for a while before coming back as faculty at the Raman Institute till about 2007, when he joined IUCAA. And in this period, he's, of course, the fellow of the Bangalore Academy as well as the NASI, and has lots of awards and prizes to his name. But the most interesting thing is that he has often worked in diverse areas, which are very interesting. And two of the major areas are, of course, neutron stars and gamma ray bursts. And this is why I think we're all looking forward to today's review of what he has to say about the magnetic fields of neutron stars. I'm handing over to Dipankar. We'll be back at the end of the talk for questions in the usual format when people raise their hands. Otherwise, I'd encourage you, because there's a large number of participants today, to keep your questions till the end. Thank you. Bye.
So good afternoon, everybody, and thank you very much, Somak, for that nice introduction, and thank you, Kandu, for asking me to give this talk, and also sort of helping make up my mind as to what the subject, the colloquium should be. So, I will talk about the magnetic fields of neutron stars, and this is a subject that I have off and on worked on for a fairly long time, right, from the beginning almost. Although the activity has sort of ebbed and flowed over time, this still remains a very interesting subject. And so what I would like to give you today is a sort of a run through of the development of the subject over time. In fact, this kind of chronological coverage helps understand the development in a proper context. Sometimes just faced with the recent results, one may feel somewhat lost as to why some assumption was made and why some direction has been pursued. So consider this talk as a review or survey of the evolution of ideas in this area. So some key points to start with to introduce the primary issues in the neutron star magnetic fields. First of all, neutron stars do have the strongest magnetic fields that we can know and we can measure. The strength of the magnetic fields lie in the range of about 10 to the power of 8 Gauss to about 10 to the power of 15 Gauss. It's a fairly large range, but it's also the strongest values that we have measured in the universe. What is the origin of these fields remains an open question, and that is one of the questions that people have been asking for a very long time. But either the origin or the evolution or the mechanism of evolution, they still remain open questions. There are no definitive answers as yet. So what I would like to do is to just list the various ideas which people have proposed. Most of them contain very interesting physics, so it is important and interesting to go through them. So we'll come to that in a moment. So let's take a look at certain important points regarding neutron star magnetic fields. Other than the fact that they are the strongest fields known, there is a big range in these magnetic fields of about more than a factor of 10 million. But how do we know what these field strengths are? So measurement of these field strengths are often somewhat indirect. So there are three main methods which people use to measure magnetic fields. The large majority of them are measured for radio pulsars. That is the form in which most of the neutron stars are known. And these pulsars are spinning down due to magnetospheric torque. And assuming this magnetospheric torque has dipole-like nature, one can convert the measured spin down rate and the spin to the strength of the magnetic moment. And that is one of the key measurement methods of the magnetic fields of neutron stars. In a few cases where the circumstances are right, the magnetic field strength is in the right ballpark, and the neutron star is accreting matter from a companion star, then you can sometimes see in the X-ray spectrum of the neutron star some absorption lines which are the cyclotron resonance features. Now, since cyclotron resonance features have energies proportional to the magnetic field, so once you have detected a cyclotron line, you can measure the magnetic field in the region in which the X-ray spectrum is originating. And often that is very close to the surface of the neutron star. So therefore, you have an estimate of magnetic fields close to the surface of the neutron star. A somewhat more indirect method is the torque that the matter accreting on the neutron star exerts on the neutron star itself, and that is the torque is exerted via the magnetic field interacting with the incoming matter. The incoming matter will have angular momentum because it often comes in an accretion disk, and in the disk magnetosphere interaction, one can estimate how much accretion torque is being exerted on the neutron star. The spin up that this torque creates on the neutron star, that can be measured, and coupled with the measurement of the X-ray luminosity, which is also an indicator of the accretion rate, eventually this can be led to give you a measure of the magnetic field strength or magnetic moment. Also, if you have some independent measure of the size of the inner edge of the accretion disk, because the stronger the field, the accretion flow is interrupted the further away from the neutron star by the magnetic field. So a measure of the inner edge of the accretion disk can also give you some estimate of the magnetic field of the neutron star. So a mixture of all these techniques are used to determine the magnetic fields of neutron stars. And the figure on the right displays most of the magnetic field measurements that we have today. This figure is taken from the review by Sushant Konar in Journal of Astrophysics and Astronomy in 2017. And she has nicely compiled all species of neutron stars that we know in this diagram. It's highly rich in information. The gray points here are the radio pulsars. There are a large number of them. So it's plotted with the symbols, which are small and gray. The open gray circles are the radio pulsars in binary systems. Small gray dots are isolated radio pulsars. And then there are various other types of neutron stars. For example, accreting neutron stars in binary systems, high mass X-ray binaries over here, where magnetic field is measured from cyclotron lines. Then there are these magnetars, which are very strong magnetic fields. And in magnetars, the energy that the neutron star emits and the radiation that we see comes at the expense not of the rotation largely, because but at the expense of its magnetic field. So magnetic field is being used also to power these objects. Magnetic field energy is being used to emit the radiation we see. So what other relevant information do we have from measurements? Measurements of radio pulsars tell us that the magnetic field is largely dipole in the radio emission region that we see. And the magnetic moment is not aligned with spin. So the magnetic field, the origin of the magnetic field is not intimately tied with the spin itself. So magnetic moment has a sort of uniform distribution of angles with respect to the spin axis. So they could be anywhere. Now, there is a large diversity of field strengths that we see from this diagram. And as I also mentioned before, the horizontal axis here is spin period, and the vertical axis is magnetic field. And you can see that these objects do not fill this diagram uniformly, but they form a certain narrow distribution over here. And the question is why this is so. Does the range of field strengths represent the neutron star fields at birth and distribution of those? Or is there an evolutionary connection between neutron stars born with certain fields and then end up by evolution somewhere else in this diagram as the time passes or as the circumstances change? So this is a creationist versus evolutionist debate that has been on for a long time. But the indications are that evolution does play a major role in deciding this large extent of the field, particularly at the low field end. We will come to that as we progress through this talk. Now, if evolution is indeed happening, then the evolution actually depends on how the field is distributed inside, where it is located, what its strengths are at various places. So the evolution may provide clues to the origin and internal distribution of the field itself. Now, magnetars, I said, expend their magnetic energy to produce radiation, then obviously their magnetic fields have to evolve. And without that, you will not be able to power them. So clearly at that end, we know that the magnetic fields are evolving. And it is true that even in these other cases, we will see that magnetic field evolution is strongly indicated. So let us now look at what people have thought about the possible origin of neutron star magnetic fields. Now, the magnetic fields, to have a magnetic field, either you should have a current, a set of currents and the distributed currents through the interior of the object, which produce the net magnetic moment. Or you can have elementary particles and their magnetic moments lining up. For example, if neutrons, all neutrons in the neutron star line up, their magnetic moments will add up to give you a very strong magnetic field of the order of 10 to the power of 16 Gauss at the surface. So it is possible that if you do line up the magnetic moments of all the elementary particles involved, or a large fraction of them, then you can easily explain the strong fields that are seen. And this was, in fact, the very first idea which was in the literature early. And people have, so a ferromagnetic transition, in other words, of neutrons. But people have shown that this is not a very likely scenario, particularly the ferromagnetism of neutrons have strong inhibitors, and the subject has gone back and forth on this. Later on, the spin alignment idea has been revived in a different context. In the very core of the neutron star, there could be a phase of nucleon-like matter, nucleon-like condensate from quarks, and there you could get partially phase, spin-aligned phase, and that could give you strong magnetic moments as well. So this remains an idea which has been talked about off and on. But one issue with this is that if you do have magnetic fields which come by spin alignment, then once the spin alignment happens, it would be very hard to knock it off. So therefore, changing the magnetic field over time is unlikely of the component in which the spin alignment has happened. So, so it needs to be folded in with other bits of the scenario to explain the diversity of the magnetic fields that we see. Another idea which has existed from, in fact, before the discovery of pulsars, and that is the flux conservation from the progenitor. So the progenitor stars usually will have significant magnetic field in the core. And if you take material such as that and compress it to neutron star densities, flux conservation will easily produce the strong magnetic field that we observe in neutron stars. So you don't need to really invent a particular mechanism for the generation of the neutron star magnetic field, but it could just be inherited from the progenitor. However, even if the magnetic field is inherited from the progenitor, in the neutron star, it needs to be sustained in a certain manner. So it has to have the corresponding currents and so on distributed through the interior, which will retain the magnetic moment that you inherit. On the other hand, there has also been suggestion that the inherited component may be not dominant, but there could be a fast convective dynamo that works during core collapse in the process of formation of the neutron star. And that dynamo could produce very strong magnetic fields, and part of which remains when the dust settles, and that is the neutron star magnetic field that we see. This was already indicated earlier, around in the 1970s, but it was revived again in the context of magnetars in the 90s. Then there is a very different mechanism which people have talked about, where only the crust is involved. The full star is does not participate in this process, and that is a thermoelectric amplification of some small pre-existing field. So here, the idea is the following. The neutron star is born hot. It is hotter in the interior than at the surface. The outer parts of the neutron star consists of a solid crust, which is made up of nuclei and electrons flowing through them. So as heat escapes from the interior of the neutron star to the outside, the electrons in the crust carry that heat as a conductor. So if you imagine imaginary surface at a certain radius, you have hotter electrons coming from a larger depth crossing that surface, and the colder electrons from above going in. And if there is a pre-existing horizontal field, these flows will be deflected horizontally due to Lorentz force. And since there is a difference in the energy of these electrons, those coming from above versus those coming from below, so this horizontally, this produces a from the vertical heat gradient or radial heat gradient, it produces a horizontal heat gradient or horizontal temperature gradient. So this temperature gradient will then generate a pressure gradient, and this pressure gradient will then be balanced by a electric field, which is the thermoelectric effect in this case. So this thermoelectric effect will have an EMF. This is not curl free, and this can be used to generate magnetic fields in loops which are of the size of the depth of the crustal material in which this process is happening. And then over time, these loops can join up and make large-scale fields. So this is a mechanism which was first proposed in the Soviet Union by Urpin and Yakovlev and elaborated on by Blanford, Applegate, and Hörnquist in 1983. The key difference at the end of this mechanism operating will be that the magnetic field will be resident in the crust alone. This strong magnetic field, which we see outside, will not penetrate through the crust core barrier and go inside. So the core certainly will not have the benefit of the magnetic field that was generated through this process. So you get a crustal magnetic field here. So that means all the currents that are generated are confined to the crust. On the other hand, for these other mechanisms we talked about, the currents and the charge carriers are likely to be distributed all through the neutron star, including the core. So before we go further forward, let me say a few words about the structure of a neutron star. I already mentioned that the neutron star has a crust. The crust has two parts to it. One is outer crust, which is composed of nuclei and electrons. So the nuclei sit as ions in a lattice, and the electrons are itinerant through this lattice, so like a metal. Then as the density increases above about 10 to the power of 11 grams per cubic centimeter, the inner part of the crust has nuclei in lattice, but it also has free neutrons. So you have crust, you have nuclei in a lattice, you have free electrons, and you have free neutrons. So, and then there comes a boundary beyond which the nuclei no longer exist. All nuclei dissolve, and you have only free neutron, protons, and electrons, and that is the core. And at the very inner part of the core, the composition is still unknown because the equation of state is still not fully understood. So this large part of this neutron star, which is in the outer core, is composed mainly of free neutrons, free protons, free electrons, and free muons. And in this entire region, where free nucleons exist, because of the strong interaction between them and the relatively low temperature, so the temperatures in the neutron star interior are less than, say, about 10 to the power of 9 Kelvin, so less than about 0.1 MeV. So at those temperatures, neutrons and protons can pair with them among themselves and form Cooper pairs and form condensates. So neutrons exist in the form of a superfluid, protons form a superconductor, and in the inner crust, where free neutrons exist but not free protons, we have a neutron superfluid. The interior of the neutron star therefore consists of a large amount of condensate, neutron superfluid and proton superconductor. And that has important implications in the both the existence and the evolution of the magnetic field. So just a quick introduction to what happens if you have rotation and magnetic field in the superfluid superconducting interior. A superfluid cannot carry rotation. A superconductor conductor cannot carry magnetic field in itself. So a superfluid carries rotation by creating vortices, quantized vortices, each with a vorticity quantum of h over twice the mass of the neutron. And the core of the vortex is normal. And there is a 1 over r superfluid velocity field, rotational velocity field, around the core. And the magnetic field in a superconducting proton interior also cannot be carried by the superconductor itself. So it is carried in fluxoids, where the fluxoids again are normal, so it is non-superconducting. So each fluxoid carries a flux quantum of hc over 2e, and around that there is a screening supercurrent which falls, which screens the magnetic field exponentially over a length called the London length. So neutron superfluid energy gap is about 1 MeV, and neutron star interior temperature are much lower than that, and it's even lower likely compared to the proton superconductor energy gap, which is about 1/10 of an MeV, estimated to be about 1/10 of an MeV or so. So given this, the proton superconductor turns out to be a type 2 superconductor, where you have a lower critical field, which is about 3 orders of magnitude less than the upper critical field. And it is in this intervening region that in a normal type 2 superconductor, field can be carried in fluxoid-like structures. If the field inside happens to be below the lower critical field, then the normal tendency of the superconductor is, by Meissner effect, to expel the field from its body and then just move it to the periphery of it. However, the situation is somewhat different in the case of neutron star interior, because the interior contains not only one species of charge, which is protons and which form a superconductor, it is co-located with an electron component, and the electron component is not in a superconducting state. It is in a normal state. And if you want to do a Meissner expulsion of magnetic field, even if the field happens to be lower than the lower critical field of 10 to the power 14 Gauss, it has to move through the electron component. And because the electron component is normal and is highly conducting, moving magnetic field through the electron component is very hard. It takes a very long time, much longer than the proton superconductivity to set in and be threaded with the magnetic field. So regardless of the fact that the interior field could be even less than the lower critical field, you would still have proton fluxoids carrying the field through them. Now, neutron vortices carry rotation, but interestingly, since this neutron fluid coexists with the proton fluid, and as far as strong interaction is concerned, they just have different isospin, but the interaction is symmetric. The superfluid velocity field, the neutrons, will also drag protons with them. And this superfluid drag will cause a proton supercurrent around the neutron vortex. And this proton current can generate a strong magnetic field through the normal core of the vortex. And interestingly, the estimated value of this magnetic field at the interior of the neutron vortex is about 10 to the power of 15 Gauss, which is also the core field inside a proton fluxoid. So if you have, let us say, a non-magnetic neutron star, which is simply rotating, and you have the neutron vortices, then these neutron vortices will actually generate a magnetic field which is aligned with the spin of the neutron star, which is aligned with the vortices. However, the magnitude of this field is quite small. Although each vortex carries almost as much magnetic field as a proton fluxoid, there are far fewer of them. The number of vortices in the neutron star interior for a neutron star spinning at about 1 second is about 10 to the power of 15. So if it is spinning at a millisecond, then it will be about 10 to the power of 18. Whereas the number of fluxoids that you need to carry a magnetic field of 10 to the power of 12 Gauss is about 10 to the power of 31. So the net magnetic field the neutron vortices alone can produce for a millisecond pulsar, for example, is about 10 to the power of minus 4 Gauss, which is aligned with the spin of the neutron star. So this is not of consequence in the magnetic phenomena that of neutron star that we see. So it is an interesting aside that this rotating neutron star will get magnetized even in absence of any other source of field. But the fields that we see are not caused by this process. However, the strong magnetic field of the neutron vortex and the proton fluxoid, they can interact and interesting things can happen, which we will come to at a later point. So let us look at the contributing physical processes that could lead to evolution of the magnetic field. So let's start with dissipative processes. The most common dissipative process we know is ohmic diffusion. So if the conductivity of the star is low enough, then within the observable time scale, you should see significant ohmic diffusion. However, if the currents are in the interior of the neutron star, in the core region, the conductivity in the neutron star core is very high. The ohmic timescales far exceed the Hubble timescale. So therefore, if currents are sitting in the core and the current loops are as large as the stellar size, then you don't expect ohmic processes to contribute much to the neutron star evolution. However, in the crust, ohmic processes are relevant. The conductivity happens to be a strong function of density and temperature. So I've plotted schematically the run of conductivity as a function of depth in the crust. So this is near the surface, this is 10 meters. This is the bottom of the crust, about 1,000 meters. And you can see that the conductivity rises by a very large amount. So, and I have also plotted this for 3 different temperatures, 10 to the 6 Kelvin, 10 to the 7 Kelvin, 10 to the 8 Kelvin. And you can see the strong dependence on temperature as well. Just to give you an idea as to what this means regarding the ohmic evolutionary timescales, I have plotted on the right-hand side the ohmic timescale in years, logarithmic of ohmic timescale in years, for current loops of the size of 10 kilometers. So at the outer crust, outer regions of the crust, you can see that a few million years, you can even get less than a few million years time scale at which currents could decay. As you go further down in the crust, the time scales increase dramatically, but and at the bottom of the crust, the time scales would exceed the Hubble time. For current loops, which are about 10 kilometer in size. However, you could have smaller current loops, and the time scale goes down a square of the size of the current loop if you make it smaller. So, for example, if it's a 1 kilometer size, then the time scale will be 100 times smaller, and so on. So, in the crust, therefore, the ohmic process does remain relevant within the evolutionary timescales that we experience. Then another process which is important in the core as well as in the crust, and that is ambipolar diffusion. And that is when the magnetic field is trying to relax to a certain configuration by reconfiguring itself by bodily moving. Then the magnetic field moves to the charge carriers, and the charge carriers are protons and electrons. And as the charge carriers move, since there is a large number of neutrons, the neutrons dominate the interior, the scattering of the charge carriers from the neutrons, which are the neutral particles here, will drain energy, and this will reduce the strength of the current. It will drain the magnetic energy. So that is a dissipative process which can reduce the strength of the magnetic field. The third dissipative process, which can reduce the energy of the magnetic field and radiate it away, is in fact the IUCAA process. In a situation similar to what I described, where the magnetic field is trying to reconfigure itself, and charged particles, for example, the proton-electron component, is moving from its undisturbed location, then if you make a change in the distribution of protons in the interior of the neutron star, then you will get an imbalance of the beta equilibrium, because the structure of the neutron star is determined by the local beta equilibrium at every place. So that is the chemical potential of the neutron equals the sum of the chemical potential of the proton and the electron. I'm leaving out muons in this discussion, let us say. So, so that will get imbalanced if you change the density of the protons. So this kind of motion can only therefore happen if this balance is restored by transmutation of the species. So the neutrons have to change into protons and vice versa. And this transmutation of species happens through this IUCAA process. There is a direct IUCAA process where neutrons can just decay into protons and electrons and produce antineutrinos, or proton can combine with an electron and produce a neutron and a neutrino. So that's a direct IUCAA process. These neutrinos and antineutrinos escape from the system, carrying the energy. Now, this direct IUCAA process is possible only if the proton density in the interior exceeds about 10 to 15% or so, more than 10%. Otherwise, modified IUCAA process operates, where two particles have to come together, neutron plus neutron. They scatter each other and then produce this neutron, proton, electron antineutrino, or neutron, proton, electron come together and produce neutron and neutron and neutrino. And similar process with protons. So because this involves one additional species of particles involved in the interaction, the process is, has a much lower rate. And so, but even this could be a serious drain on the energy of the system. So either direct IUCAA or modified IUCAA will restore the chemical potential imbalance that would be caused by displacing the charge carriers with respect to the neutrals. And as that happens, the magnetic field can move and migrate in the interior. So if you look at the energy dissipation rate in the interior, it is a combination of this IUCAA term, where this is the chemical potential imbalance, and this is the reaction rate, IUCAA reaction rate. This is the ohmic rate, and this is the ambipolar rate. This is the difference in the velocity between the neutron and the proton, and this is the scattering rate. So you integrate this over the volume, and that gives you a rate of loss of magnetic energy. And in case of magnetars, for example, it is energy loss of this kind that can power the emission and keep the surface hot and produce the X-rays that you see. So that's about dissipative processes. Then there are processes which lead to migration and reconfiguration of the magnetic field. First of them is, of course, MHD or plasma motion. If the field is not in a force equilibrium configuration, of course, fluid velocity is induced, and fluid will move in typically Alfvén timescale. If the initial configuration of the magnetic field has twists, then over time these twists can relax. Crust quakes can happen because of this, and even reconnections can happen if the conditions are right. And all of these have been invoked to power some of the magnetar emission. And fluid velocities reconfiguring the field could be important in the very initial minutes of the birth of the neutron star. So you can have, let us say, if you start with a purely poloidal magnetic field, because of this MHD and plasma motion, the material can overturn and the magnetic moment can reduce. If there is nothing to arrest it, and if there was no helicity in the original magnetic field that we impose, then the final poloidal field can end up being almost zero. However, there are possibilities that the inherited field does have some helicity. And secondly, as the overturn continues, at some point, the crust of the neutron star freezes and becomes solid. And then the overturn will stop, and the magnetic field will freeze in that configuration. And that can happen within minutes after the formation of the neutron star. So whatever field configuration can change during that, until that happens, will take place. And once the crust is formed, we have a frozen magnetic field. So, so that's bodily movement of material. But reconfiguration of current configurations can also happen due to, for example, Hall drift. So let's say the crust where the charge carrier electrons are moving in the background of fixed ions, and there is magnetic field. So the electrons feel the Lorentz force, and this Lorentz force then acts on the electrons and modifies the current distribution. And so this is the modification due to Hall effect. This will continue until this forces, all forces on the electrons balance, and then you will get a final magnetic field configuration. The suggestion around early 90s was that the Hall drift of this kind can create from a large scale current distribution small current loops, break it up into small current loops. And if you make current loops small, then the ohmic decay rate can increase, because the ohmic time scale is proportional to the square of the length of the current loop. So this was an idea which was proposed in 1992 by Goldreich and Reisenegger. It has been investigated in detail later. I will come to some of the results further during the talk. Then the other possible effects include in the core, you have the proton fluxoids. They can drift through the core, because at the core of the fluxoids, the density is smaller than the outside. And that's because part of the pressure is provided by the magnetic field. It's in pressure equilibrium, so density is lower, so it is buoyant and it can rise. However, such motion is also opposed by scattering with electrons and other such effects, as well as any bodily motion of such carriers, as I mentioned earlier, will have to proceed in the time scale in which you can restore beta equilibrium. So regulated by that, buoyancy can work. And I also mentioned the neutron vortices can couple to proton fluxoids, and neutron vortices move because if the neutron star spin angular momentum is changing, then the neutron vortices will move. If the spin angular momentum is going down, then the neutron vortices will move out. And as the neutron vortices move out, they may interact with fluxoids and make them migrate as well. What I've written below is an induction equation with terms clearly indicated of what the MHD motion, Hall motion, and the ohmic motion. So it's just for reference. Another effect which has been of great interest, I should say, in literature is screening of the magnetic field. So here you accrete material on the neutron star from outside. So the intrinsic magnetic moment of the neutron star is not relevant whether it is affected, but the material which comes in is very strongly conducting, and as the material accretes on the surface, a screening current is generated through this material, and this material then buries the magnetic field in the sense that magnetic field lines do not cross this material. They will close inside, and the external observer will see a reduced magnetic moment. Now, this buried magnetic moment, magnetic field remains under the material that has been accreted, and it may be subject to further evolution. And similar context has been invoked for rather inert neutron stars, which have been seen in newly born neutron stars, which have been seen at the cores of supernova remnants. They're called central compact objects. They are bright in X-rays, but they don't produce pulsations. So the conjecture is that in the final stage of supernova explosion, some material from the inner mantle of the progenitor star fell back onto the CCLs, and it has buried the magnetic field, probably temporarily. And after some point, this field will then, due to ohmic diffusion, plow through this material and then emerge at the surface, and these will turn on as pulsars. And some of the pulsars are actually seen if you look at the second derivative of its spin period. Its magnetic field appears to be increasing and then eventually could attain magnetar fields. So perhaps the CCOs will eventually become pulsars and eventually go towards magnetars. So that is also an evolution that will happen through this buried field. There is an idea which has been proposed, which I alluded to initially, that you could have a phase transition to a spin-aligned state in the very inner part of the neutron star, in the inner core. Now, if this happens after the neutron star formation, then as the inner core spin aligns, its magnetic field will rise. However, the outer parts, which are around this inner core, there will be screening currents generated in it. So an external observer actually will not see this enhanced magnetic moment which has been generated in the inner core. Over time, dissipation of these screening currents will cause the surface field strength to rise. So this also has been used in some scenarios to generate magnetar fields. So these are processes which can produce evolution of the magnetic field. What do observations tell us? So let's look at now the observational evidence, what we know from it. The very first idea of magnetic field evolution for pulsars was spontaneous field decay. Pulsars have been known for 50 years. For half that time, people believed that the neutron star magnetic fields decay in about a million-year timescale spontaneously. So where did this idea come from? So initially, only with a few pulsars, the estimate of the magnetic field from the spin and spin down rate, the magnetic field square is proportional to P times P dot. When compared against a time scale, which is period divided by spin down rate, showed an anti-correlation. However, it was quickly realized that this is actually not a tenable conclusion, because of the very much larger range of P dot than P. This way, what you end up actually comparing is P dot versus 1 over P dot. So this anti-correlation is partly or largely artificial. So this is not a real argument, but the argument that really was quite strong for a very long time, and that is the comparison of the kinetic age versus characteristic age. So if you take the height of the position of a neutron star above the galactic plane and divide it by estimated vertical velocity, then you can get an age of this neutron star from just its kinematic measurement. So that's the kinetic age. If you plot it against the spin down age, then what people found is that while the spin down age keeps increasing to fairly large values, to 100 million years or so, the kinetic age does not increase very much. So that means the pulsars that we are seeing, their real age, which could be the kinetic age, is limited to about a few million years, whereas the spin down age, which is determined by computing the spin down, measuring the spin down rate, increases much more. And this could be very easily explained if the magnetic field is decaying with a few million year time scale, because then the P dot drops dramatically and the P over P dot increases. So this stuck as a very clear indicator of the magnetic field decay until sometime when certain new discoveries happened. I'll come to in a moment. So this is also related to the distribution of the pulsars away from the galactic plane. So here in blue are plotted the expected trajectories of pulsars given their velocities, but in red are plotted where the pulsars actually are, as estimated by the pre-1991 distance model. And you see that they are all close to the galactic plane. You could have seen them even further away, but you don't. And this was taken as an indicator, as the fact that because the fields disappear, so the pulsars stop functioning, so we don't see them far away. So let me move forward from here. Now this argument got turned on its head once some pulsars in globular clusters were discovered. So there, what one found is that the dispersion measure, which is used to measure the distance to the pulsars, actually, if you take the vertical component of the dispersion measure distance, that stopped increasing after about 1 kiloparsec or so. So which means the electron layer, which is used to measure the distance, was not of infinite extent, but had a scale height of about 1 kiloparsec. So that means those pulsars, which we thought were very close to the surface, galactic plane, within a kiloparsec or so, could actually be much higher, but because we cannot measure the distances beyond a certain distance, we erroneously think that they are close. So if you now use a more modern distance model, then you see that pulsar distribution is much wider, and for some cases, you can only measure the lower limit to the distance. So therefore, this entire argument of kinetic age versus characteristic age disappeared, as also the vertical distribution of pulsars. And when put all of these things together and then do a detailed population synthesis study, you find no evidence of spontaneous field decay. But one thing remains, that if you look at the pulsars in binary systems, then their magnetic fields are much lower than the magnetic fields of isolated pulsars. And here is a distribution diagram. So it looks like the magnetic fields do decay, but they're more related to binary systems. Now, there are other individual measurements of very few binary systems where secular field evolution is seen. One is the Hercules X1, where the magnetic field was seen to drop for a while, and now it seems to have leveled off. But there is an earlier episode of the magnetic field rising in this binary as well. There is another binary system where magnetic field was seen to suddenly drop during accretion by a factor of 7 or so over 3 months, and then leveled off. So binaries do have significant impact on the magnetic field of neutron stars. That's what it appears. So how does this take place? So first, a few words about magnetic fields in the core. So magnetic field in the core can show substantial evolution because of reconfiguration. But the reconfiguration leads to what is called Grad-Safronov equilibria, where the sum of the forces due to magnetic field, the gravitational potential, as well as the nuclear forces, they balance. And after that, there is no major evolution. So here it shows some degree of evolution of the magnetic field, which happens due to this, but there is no great degree of evolution that you see due to this. You do have about half the magnetic energy which can be extracted out of this, which is quite substantial, by the way. But the very large change of magnetic field does not happen by orders of magnitude. The crustal evolution due to Hall effect also does something similar. It drives the configuration to an attractor state, where no matter what initial field you start with, you seem to come to this attractor state where the electron azimuthal velocities are constant on poloidal field lines. So, and in the process, you actually do not generate very small current loops. You do not enhance the ohmic decay very much. If the currents are confined to a very outer range of the crust, then ohmic evolution can give you about a couple of orders of magnitude of decay, but not by 3 to 4 orders of magnitude, which we see in binary systems. So in binary system, a neutron star can experience some additional things. Aging, of course, which we discarded as a pure cause of magnetic field decay. It can have sustained heating due to mass accretion. There is strong spin evolution, and you can have covering of the original surface by accreted matter. All of these could affect the magnetic field, and all of these have been explored. This is actually work in Sushant Kunar's thesis, where she showed that the incoming matter settling on the surface of the neutron star can heat the crust up enough. So if you have a crustal field, it will decay substantially. However, this incoming matter also pushes the current into a more highly conducting region to higher densities, and at some point, therefore, the decay freezes. So depending on what the initial depth of the field was, or what the accretion rate is, you can get different levels at which the field freezes off. The connection between vortex and magnetic field can also cause very significant change if it works in the magnetic field configuration in the interior. In a binary system, the spin of the neutron star can undergo very large evolution, starting with dipole spin down, then stellar wind, then in Roche-Loeb overflow in mass accretion. it can spin up. And in this major spin down process, the vortices will migrate outside, and if they are carrying the fluxoids with them, they will deposit the crust in the base of the deposit the flux at the base of the crust, and they can then undergo decay over time, depending on what is the decay time in the crust. And this simulation by Jahan Miri and myself that we did showed that yes, indeed, such a thing can reproduce the magnetic fields, residual magnetic fields, after a long time in these binary systems. Finally, the accretion which happens on the poles of neutron stars, whether they will, that matter when it spreads over the neutron star, whether it will carry the magnetic field and bury under it, that remains a question under active investigation. What we know is that initially the accreted matter will form a mound, and this mound can expand. And in some calculations like this by Penn and Melatos, they seem to find that there is a large decrement of the external magnetic moment that we'll see in this case. However, no instabilities are accounted for in this. Dipankar Mukherjee in his thesis investigated this, and he first calculated this Grad-Safronov equilibria, which gives you the shapes of these mounds, and then subjected them to perturbations, and then looked at what kind of instabilities grow in them. And he finds clearly that once the mound height grows over a certain value, you trigger instabilities, and these instabilities can cause interchange instabilities at the edge, and the matter can leak out without significantly distorting the magnetic field over long term. So long-term burial of the magnetic field, although it remains a most popular scenario in the literature, but when you look at the physics, it does appear difficult. To summarize then, we have said that the neutron stars possess the strongest magnetic fields known, but no definitive answers yet as to how they originate and evolve. A fascinating interplay of various physical processes which I have described govern the magnetic field evolution. And mechanisms involving Lorentz forces appear to drive the system to hydromagnetic equilibria. It could be either the Grad-Safronov equilibrium in the interior or Hall equilibria in the crust. And evolution of the binary system does appear to cause significant magnetic field decay. What exactly is the cause? There are several probable causes. What exactly it is still remains to be identified. In future prospects, we would say better observational probes of polar cap accretion and the related magnetic field evolution will happen over time. Extensive long-term follow-up of rapidly evolving objects, including magnetas, all the selected pulsars, X-ray binaries, transitional millisecond pulsars would be very interesting. Magnetar seismology, which may develop over time, could reveal the distribution of subsurface magnetic fields. And theoretical computations need to further develop. The computer simulations, numerical calculations will need to become more comprehensive, and the role of the superfluid and superconductor needs to be explored in greater detail. So there's a lot of work to do. This is still a very fascinating subject. Thank you very much.
Thanks very much. Thank you. It was a very wide sweep review of a very, very interesting topic, and I'm sure there'll be lots of questions. Please put your hand up for questions. Go to the participants window and use the raise hand option. Yes, Bhaskar Bishash to begin with. I am unmuting you. Go ahead, ask your question.
Hi, so any rotating neutron star actually they are unstable because of CFS instability, and because of this instability the spin of the neutron star actually goes down. So can that type of instability also affect the evolution of magnetic field?
Yeah, so this is for a very, very fast rotation, of course, near breakup period where CFS instability occurs. any structural change in the neutron star will also, of course, affect the magnetic field. So exactly what the effect is going to be will depend on the distribution of the field in the interior and how the currents are made to move because of such instability. But this is not really relevant for most of the neutron stars that I talked about, because they are not really near that breakup or CFS limit.
Okay, thanks.
Great, thanks. So next one, Shantanu Desai, unmuting you.
Yeah, so what is the mean energy of the neutrinos which happen due to the IUCAA process, and what does it depend upon? Mean
those are
peak
the,
energy.
those will be the thermal neutrinos, because they will have actually a thermal spectrum and with a temperature of about close to an MeV or so.
Okay. Okay, thank you.
Great, Shantanu. Thanks. Thank you. Next, I think Bhattacharya's hands up. Unmuting you.
Thank you. It was an excellent overview of magnetic fields in neutron stars. I have a couple of comments where you mentioned the different possible origins of magnetic fields, like you mentioned also in the conclusions that this is still an open question. This is being probed by many different theories. I would like to mention here that there is also this recent interesting work from Martin Obergaulinger and group in University of Valencia, where they look at magnetorotational instabilities in proton-neutron stars. And although they inject 10 to the 15 Gauss magnetic fields for their nonlinear simulations, but they also propose this as one of the possible origins of magnetic fields in magnetars.
Yeah, so you are right. Now, I did not go into the details of it. I would classify it, I would rather club it in the classification of dynamos. So, but yes, in the dynamos also there are various shades of it, and magnetorotational instability is one of them.
Thanks. The other thing I would like to mention here, this is related to Bhaskar's question. So another thing that comes to my mind is, for example, R mode evolutions in neutron stars. Yes. So this is something like not only in the context of newly born, rapidly rotating neutron stars, but also accreting ones. And there is a very complicated evolution which depends on the amplitude of the R modes, the frequency, and the temperature. I mean, in addition to the magnetic field. So I think there is some complex evolution going on there, which is still unknown.
I agree. So most of the R mode calculations, I mean, you do that yourself, many of them are done without involving the magnetic forces. Once you take into account the magnetic forces, you can have modifications to those, and that can feed back on the magnetic field also, depending on whether you are affecting the regions where the currents producing these magnetic fields are located. If they are co-located in the same region, then yes, you can have some attendant evolution of the magnetic field itself.
Okay, thank you.
Great, thanks. Actually, co-hosts can't raise their hands, so Kandu has been gearing up to ask a question. Let Kandu go next. There are many other hands up.
Yeah. Thanks, Dipankar. I wanted to ask a naive question. That suppose you have helicity of the field in the interior, superfluid, superconducting, whatever.
Yeah.
Then do these fluxoids, can they carry helical fields?
Yeah, so fluxoids don't need to be straight. The whatever is the internal magnetic field configuration, the fluxoids will adapt to it, and there can be a complicated distribution of their geometry as well.
So you can interlink fluxoids also.
Yes, yes, you can interlink fluxoids.
And what about the superfluid turbulence? Will they also break up stuff, and if there is some turbulent stuff going on?
Superfluid turbulence, will affect the neutron component. So unless, see, the neutron component dynamically works differently compared to protons. For example, the protons can happily carry the rotation. They don't have to create vortices because it's a charge component, whereas neutrons can't. So there is a decoupling in some respects in the dynamics of the proton and the neutron component, and there is a coupling because of strong interaction.
Right.
So it will depend on the detail of the distribution of this turbulence.
Okay, we'll discuss later. Thanks.
Yeah.
Okay, other hands up. Nishant, go next. Unmuting you. Nishant, you're muted.
Oh, hi.
Yeah.
So Dipankar, just wanted to ask, do you think the chiral magnetic effects will be important?
Where in the core?
I mean, is it possible that the chiral magnetic fields be important? Or are there some preferred regions where this right and left-handed leptons are asymmetric? In which case you get a new contribution in your induction equation.
Yeah, so actually this spin-aligned states which people have talked about at the very high density, they involve chirality, not of leptons, but of quarks. So I have not come across any literature on chirality of leptons being invoked for magnetic fields of neutron stars, but I will have to understand that better.
Okay.
I don't think I can comment on this right now.
Great. Rajaram next. Rajaram is there. Unmuted you, Rajaram. Can you unmute? Yes.
Dipankar,
Hi,
I
Rajaram.
just wanted to ask a status of reviewing the kind of very theoretical or mathematical physics question. You just have a sphere of fluid, say uniform field inside, dipole field outside. You're allowed to rearrange the field in any way. Is there a lower bound to the magnetic energy? I mean, you refer to some processes which can reduce the magnetic energy. Is there a theoretical lower bound to all possible rearrangements? No physical constraints, just incompressibility.
No, but this is a structure in equilibrium, no? So it's there is hydrostatic equilibrium or hydromagnetic equilibrium.
No. So that's why I said it's almost a math-based question. Yeah, just move the fluid around.
Oh, in that,
Subject to
I don't know. I have not come across theorem in that context. But if you do have if you do apply a condition of hydromagnetic equilibrium, then there is a limit, which is this Grad-Safronov limit. That's what I mentioned.
Okay.
But if it is arbitrary and there is no force constraint on anything, then I'm not sure, because the material can explode also, no? So they can.
You keep it within the sphere. It's some map of the sphere into itself. But as I said, it's a fairly mathematical question.
Okay, so you don't. Okay, all right. So yeah, no, I don't know mathematical.
You might be interested to know whom I learned this question from. So it is from V.I. Arnold, who visited ISC some decades ago.
Yes.
He said doesn't know the answer. There's no lower bound. But anyway.
Right.
Thanks.
Yes. Okay, thanks.
Thanks, Rajaram. Next, I can see Indra. I don't know which Indranil this is. Unmute.
Yeah, this is from Aries. Very nice talk, Dipankar.
Thank you.
My question is slightly not exactly on this topic, but slightly away from it. The magnetic fields of neutron stars are generally, for accreting neutron stars, it's assumed it's a rigid rotator, right? I mean, it's like rotating rigidly with the neutron star. Yeah. How far is this assumption valid? Typically in terms of, say, a neutron star radius? I mean, what portion of this radius will, I mean, at what height this will start to be ineffective?
You mean inside the neutron star?
No, outside.
Oh, outside the neutron star. So outside the neutron star, of course, it depends on what is present outside. If it is pure vacuum, then you will have co-rotation until light cylinder.
Okay.
Right? But in many cases, you have this material entering from outside.
Right.
And even in radio pulsar, where you start with vacuum, you create your own magnetosphere.
Right.
And charged particles are present. Then very soon, the magnetic field is no longer a purely co-rotating entity, but it is co-rotating, all right. But it is no longer a pure original dipole shape entity. It gets distorted, and beyond, let's say, the light cylinder in a pulsar, you have particle winds which are carrying this magnetic field, and this spirals out and so on. So at the base, of course, it co-rotates.
Okay.
And then you get distorted structures because of inertial effects of whatever material comes in or goes out.
Thanks.
Yeah.
Great. I see, I don't know whether you still can take questions. I see Dipanjan's hand up. Of course, Dipanjan and Shushan, both their work featured quite a bit in the talk. Dipanjan, go ahead, ask your question.
So how can I not answer their question?
Exactly.
I'll ask a brief question. This is a very nice overview and very nice to see all these slides again. So regarding this thing about this garden variety pulsars starting off with 10 power 12 Gausses and the magnetars with really strong fields, has there been now a consensus or any link regarding the progenitor star or something regarding the progenitor that can cause these differences in magnetic fields, or is just the internal mechanisms that boost up the field for magnetars, I mean?
It is still an open question. There was some indication a little while ago that the magnetar population might be coming from more massive progenitors. So perhaps on somewhat higher mass scale when the neutron star is formed at birth. But it's very difficult to say that for sure, because for magnetars themselves, we cannot measure their masses because they are not in a binary system. And so there is no real way to do this with any certainty. But with association of supernova remnants, people have commented that the magnetar population appears to be coming from a slightly more massive range of progenitors, which may be true.
Okay. But there is no strong consensus yet.
No strong consensus. There are too few objects for which this can be done.
Great. If there are no further questions, I'm gone. No? Anybody else? Okay. Well, let's thank the speaker today, and it was a wonderful talk, and I'm really happy to have such a wonderful response after that as well. Thank you for being here. Kandu, did you want to talk about what's coming next?
No, 2 weeks from now, they will see in the notices, so it's fine.